Right, question 1, what's first of all the equation for complete combustion of cyclohexane? So cyclohexane, remember, is this. So that's C6H12, not C6H14, because it's, as soon as you make a ring, remember, you have to lose 2 hydrogens, so it's C6H12 is the formula. And that's a liquid, because it tells us that in the question, plus some oxygens will give you 6 CO2s, because you've got 6 carbons, and that's a gas. And the water, although when you burn something the water will initially be produced as steam, it says under standard conditions, and of course under standard conditions the water would be liquid, so you've got to read the question carefully. Okay, so that's your right hand side. We've just got to now figure out how many oxygens. So 6 2s are 12, plus 6 is 18 altogether, so we need 18 over here, none there, so all of them are going to be here. So that's 9O2 for that one. In part 2 it asks us how much heat is produced by the reaction. So the key to that, remember, is this expression, which you practiced a lot in the previous exercise, Q equals mc delta T. You have to remember that, that's not on your data sheet, you need to know that's the relationship. Delta T is the temperature change, C is the specific heat capacity of the material that's being heated up or cooled down, and in A-level questions that's nearly always water, and the value for that is on your data sheet. M is the one that causes problems, so M is the mass of the material that's heated up or cooled down. Okay, so that's important. It's not the mass of the material that's reacting. Generally it's the mass of the material which soaks up the heat, and again in A-level questions that's nearly always water, either a pot of water being heated by a flame, as in this question, or the water that's the solvent in a solution where the reaction is taking place. So it's important that you remember that and don't just remember it as mass. So in this case it tells us we have a pot of 100 grams of water that's being heated, so it's 100 times 4.18, which comes from your data sheet as the specific heat capacity of water, times 57.5, which is the temperature difference between what it was at the beginning and what it was at the end, so you just get that by subtraction. And if you compute those numbers you get 24035 joules. But you have to read the question carefully because it asks for it in kilojoules, which means you have to divide by 1000. So you get 24.035 kilojoules, or 24.0 if you round it to 3 significant figures. So part 3 just wants to know how many moles of cyclohexane were burned. So we've just got moles is mass over mR, and it told us that 5 grams were burned, so that's the mass, and that adds up to 84.0, so you just get 0.0595 moles for that. And then part 4 wants us now to take the numbers that we've calculated and use those to get delta H. So the relationship we're going to use for that is delta H is equal to minus Q over the moles reacted. The minus there, remember, is only there because we know it's exothermic, and we know it's exothermic because the temperature increased. Okay, so that sign of delta H depends on whether the temperature goes up or down. If it goes up, it's a negative sign. If it goes down, it's a positive sign. So in this case it's minus Q over moles, so it's minus 24.035 divided by 0.0595, which works out as minus 403 kilojoules per mole is delta H for that reaction. Part 5 then is asking us about why you don't get the right number commonly when you do simple experiments like this to measure the enthalpy change of combustion. So you have to picture this simple experiment. You know, the way you normally do it is you just have a spirit burner, so it's got a pot with the fuel in it, a wick dipping into the pot so that you can light that, and as the material burns, you know, it gets dragged up through the wick so it can carry on burning, and you can measure from the change in mass of that how much material is burned, and the heat you use to heat a pot of water like that, which in this case was 100 grams of water. So you can see really just by looking at that picture what the big problem is, which is that you're assuming that all of the heat produced by this reaction is heating the water, and that's very unlikely to be true. You know, some's obviously heating the container, but a lot of it's likely to just escape out into the surroundings. So that's the big one. That's the reason why simple experiments like this give really poor results. So heat loss to the surroundings. Don't give two aspects of that as two different reasons. Sometimes people say, oh, you know, some gets lost to the container, that's one, some gets lost to the surroundings, that's two. They won't treat that as two different things. So heat loss to the surroundings is 1 point. Another one, which is potentially a significant problem, is that you may not get complete combustion. So some of the cyclohexane might burn to produce CO2, but some of it might produce carbon monoxide or even carbon in an incomplete combustion process, and they will have different enthalpy changes. In general, they're less exothermic than complete combustion. So incomplete combustion would be a potential big issue. And a third one would be that some of the cyclohexane might simply evaporate. It might not actually react. It might simply evaporate off into the air. And obviously you would register that as a loss of mass, so you'd think, oh, that contributed to the material that was being burned, but actually it wouldn't have done. So that would be a third possible reason. Okay, so make sure you know about these experimental limitations, because they commonly ask these questions as a sort of follow-up to the calculations. So question 2 begins by asking for the systematic names for two of the compounds involved in this reaction. A lot of people didn't remember about systematic names. You may need to look back to when we did oxidation states. So if you look back at the notes and the problems we did on oxidation states, that's where we learnt to do systematic names. So PCl3 is the first one, and the point is that you can't just call it phosphorus chloride, because phosphorus doesn't always combine just with 3 chlorines, so that compound is also very common, and so you need to find a way to distinguish them. And the way you do that is with oxidation states. So you reckon that each of those chlorines is just making one bond, in which it's getting more than its fair share of the electrons, so it's a -1 oxidation state. So you get 3 lots of -1, and the phosphorus is therefore +3. So you call it phosphorus 3 chloride. Okay, so you have to remember, first of all, that that's what it means when it asks for systematic names, that you use Roman numerals to clarify the oxidation state of any element which tends to show variable oxidation states. And then it asks for the same thing for KClO3. So remember, that's going to be a potassium salt, so it's going to be potassium something. So really what you're working out is that this is K plus and this is ClO3 minus. So really what we're working out is the name of that ion, ClO3 minus. So again, we can just use the simple oxidation state rules and say, right, we've got 3 lots of -2, because oxygen in compounds is generally -2. So that takes you to -6. Overall it will be -1, because that's the charge on the ion. So to get from -6 to -1, the chlorine has to be +5. And so that compound is called potassium chlorate. Remember, the 8 is the ending there, because when you have an ion that contains a bunch of oxygens as well as an element, like sulfate, carbonate, nitrate, are the ones you're most familiar with, all of those ions contain a bunch of oxygens and they all end in 8 to indicate that fact. So this is chlorate, and it's 5 to specify which one, because again there's more than one chlorate. You can also have ClO- and ClO4-, for example, are also chlorates, and so you need to specify that this is the one, so potassium chlorate 5. Then it wanted a suggested dot and cross diagram for POCl3. There was more than one acceptable answer to this, so if you got something marked right which isn't the same as this, it doesn't mean it's been mismarked, it just means that it still obeyed all the rules. But what we're going to do here is what it actually looks like. So phosphorus needs to be in the middle, because you can't make enough bonds if you put the oxygen in the middle. So what you're going to have is phosphorus in the middle with oxygen and then 3 chlorines around it, like this. And chlorine, as we know, is in group 7, so it already has 7 outer shell electrons. It will normally just acquire 1 more to reach 8, and then it will have filled those outer p subshells, so that's where it will stop. So we're going to expect to get single bonds there and there and there, and that leaves each chlorine with 3 lone pairs. If you didn't put the lone pairs on, you didn't get the mark, because as we know, they are important. They may not be the things that are you know, most occupying your attention when you're trying to figure out what's going on here, but they've still got to be marked on there. So 3 lone pairs on each chlorine. And then when we come to oxygen, it needs to get 2 more electrons because it's group 6, so it's got 6 outer shell electrons, and it will take 2 more to reach 8. So the way it will normally do that is by forming a double bond if it's only bonded to one thing. And so that would do that. That would leave the oxygen with 2 lone pairs. And you just need to check, is that okay for the phosphorus? So that's required 5 dots, so 5 electrons from the phosphorus. And phosphorus is in group 5, so it's got 5 outer shell electrons, so that's fine. But it also gives us 10 electrons in the outer shell. Is that a problem? Well, no, because phosphorus isn't in period 2, it's in period 3. So hopefully you remember the rule that if you're in period 2, so if it had been nitrogen rather than phosphorus, you couldn't do that, because you can't have more than 8 electrons in the outer shell for period 2. And in that case, you would have had to use a dative covalent bond here to make it work. But because it's in period 3, that's the best way of describing the structure. Part C, it just wants us to balance this equation. So you can see that one thing we're stuck with is that we've got to have 3 oxygens on the left hand side because of the formula of the potassium chlorate, but there's only 1 here at the moment, so that means that's really got to be 3 to make the oxygens balance. And as soon as you do that, you realise you're going to need 3 phosphoruses and 9 chlorines, so that gives you 3 there. And then if you check out the KCl, you see that's fine, so that balances, and that's your equation. So it's relatively easy, but it's important that you got it right. Part D asks us to calculate the enthalpy change of reaction for this equation that we've written down. So enthalpy change of reaction, remember, is defined as the enthalpy change when the number of moles shown in the equation react. And the data we're given to enable us to figure that out are enthalpy changes of formation. So you need to be absolutely clear what that means. It means the enthalpy change when 1 mole of the compound is formed from the elements it's made up out of. So when we construct a cycle to do this calculation, if the data you're using are formation data, and only if they're formation data, you put elements at the bottom of the cycle to link the 2 sides. And you say, right, following the definition, if you take those elements and use them to produce these things, you can write down using these numbers what the total enthalpy change will be, and the same if you use those same elements to form these. Now you've got to take account of these balancing numbers, because that means in the reaction as written, 3 moles of PCl3 are involved, and minus 306 kilojoules per mole is the enthalpy change when just 1 mole is formed from the elements. So it's going to be minus 306 times 3 if we go from the elements to form 3 moles of PCl3 plus the enthalpy change for KClO3, which is minus 391. So you've got to add all that lot up, including the times 3 there. Okay, so just to be clear, to get the total enthalpy change to convert the elements into these things on the left hand side, you've got to take account of the balancing numbers. If you don't do that, you're always going to get these questions wrong. So because there are 3 moles of PCl3 in the equation, it's 3 lots of minus 306 and then 1 lot of minus 391, which adds up to that lot. Now we can do the same thing on the other side, because we could take the same set of elements and combine them together to make the products instead. And again, we've got the numbers to tell us what the enthalpy change for that would be. So 3 moles of POCl3 is minus 592 times 3. And we've got 1 mole of KCl, so that's minus 436. And again, we can add that lot up together, and that gives us minus 2212 kilojoules per mole. Okay, so what Hess's law is about, and the way all these problems work, is that it says that this change, which is what we're trying to find, delta H of reaction, you get the same number in terms of the enthalpy change for doing that process directly as you would do if you did it in 2 stages like that. Okay, so if you came down from here, converted these atoms back to the elements, and then converted the elements to those, if you add up delta H for those 2 steps, it comes to the same number as delta H. That's what Hess's law is. So it's easy to get those numbers because you can see this first step is just the opposite of that. Okay, so here you're going from elements to form the compounds, but now you're going the other way. You're unforming the compounds to make the elements. So all that happens is you change the sign because you're going in the opposite direction. So it's plus 1309 to come down there. Second leg of the journey is exactly the same as that. It's the same change, same direction, so same number, minus 2212. And then we just do what we said, and we get that delta RH is equal to plus 1309 minus 2212, which adds up to minus 903 kilojoules per mole. And that's the answer. So then in part E, it asks us what you would notice about the temperature if this reaction happens. So this is just testing that you understand the significance of these signs of delta H, which is really important. So remember, a negative sign means it's an exothermic reaction, because that negative sign means there's less energy now locked up in the system, and if there's less locked up in the system, it's been given out as heat. So it's an exothermic reaction, and if heat's given out, temperature goes up. Okay, so the answer is temperature rises because it's an exothermic reaction. Question 3 then starts with this reaction, and it tells us that the standard enthalpy change of reaction, which is symbolised by that, is minus 48 kilojoules per mole. First of all, it wants us to clarify what that means, that standard thing there. So you just got to remember that it means at 1 atmosphere pressure and at a temperature of 25 degrees C, unless otherwise stated. You can have standard enthalpy changes at other temperatures, provided you define what the temperature is, but if it's not specifically mentioned, then it's 25 degrees C. Okay, so then we have some enthalpy changes of combustion, again under standard conditions, and what it asks us to do is to find the missing enthalpy change of combustion, which is for that one. So again, we're going to set up a cycle, but it's really important to be clear, these are combustion data, not formation data. So you don't put elements at the bottom, you only put elements at the bottom of the cycle if it's enthalpy changes of formation that you're using. If it's enthalpy changes of combustion, as it is here, then you put the combustion products at the bottom of the cycle, which would mean CO2 and water. And combustion is the reaction in which these compounds, or elements in that case, burn and turn into the combustion products. So the data are going to be relating to arrows going in that direction. Okay, this burns and turns into those. These burn and turns into those. Okay, so make sure you get the arrows in the right direction. So let's put some numbers on here. Reaction across the top we've got is -48. Coming down here, if we burn 1 mole of benzene, that's -3273. And we're burning 2 moles of hydrogen. Again, you ignore those balancing numbers at your peril because it will mess your numbers up. Okay, each mole of hydrogen when it burns gives you -286, but you've got 2 moles, so it's -286 times 2. And that lot adds up to -3845 kilojoules going down there. Now this one is the one we don't know, so we call it X. And when you do that, you should put a little definition in to say let X equal enthalpy change of combustion, which you can write like that for short, of cyclohexene. So then everybody knows what this X that's mysteriously appeared represents. Okay, so then we invoke Hess's law again and say, right, this, which is the direct process of benzene reacting with hydrogen, -48 kilojoules per mole. And if we did that in 2 steps, the sum of those 2 steps would also add up to -48 kilojoules per mole. So putting that together as an algebraic expression, we've got that -48 is equal to -3845 for the first leg. Okay, because that arrow is going the same way as the data arrow that we put on, so we keep the sign the same. But then the second leg is going the opposite way from this one, so it's -x. Okay, because it's +x is delta H of combustion going that way, but we're sort of uncombusting and going up that way, so we change the sign, so it's -x. And so we can simply rearrange that and get that x is equal to -3845 plus 48, which works out as -3797 kilojoules per mole.